Dear students, welcome to my third class on Module 2, Conformal Transformation and Complex Integration. In this lecture video, we're gonna see about Cauchy's theorem, consequences of Cauchy's theorem, and problems on Cauchy's theorem. To know about Cauchy's theorem, we should know the basic concept of Green's theorem in a plane also. The statement is, if R is a closed region of the xy plane bounded by a simple closed curve C, and if m and n are two continuous functions of x and y having continuous first order partial derivatives in the region R, then it is given by the integral over the region C m dx plus n dy is equal to double integral over the region R dou n by dou x minus dou m by dou y into dx dy. Cauchy's theorem statement is, if f of z is analytic at all points inside and on a simple closed curve C, then we have to prove that the integral over the region C f of z dz is equal to 0. So since they have given that the function f of z is analytic, so take the function f of z as a complex variable, that is u plus iv. So now I am going to apply the integration on both sides with respect to z. So we will get the integration over the region C f of z dz is equal to integration over the region C u plus iv into dx plus I dy. Now by multiplying both, we will be getting u into dx plus u into I dy plus I into v dx plus iv into I dy. So by multiplying I into I, will be getting I square. It will become minus 1. So I got the equation. The integral over the region C f of z dz, integral over the region C u dx minus v dy, taking all the real part one side, plus I into the integral over the region C v dx plus u dy. So call this one as equation number 1. Now, from the statement of Green's theorem in a plane, we have the integral over the region C m dx plus n dy is equal to double integration over the region R dou n by dou x minus dou m by dou y into dx dy. So now I am going to compare both the equations. So by comparing the first equation with the Green's theorem statement, we can say that u is equal to m and v is equal to minus n. N is equal to minus v. So in this equation, we can able to replace n as minus v and m as u. Similarly, by comparing this second equation with the Green's theorem statement, we can say that m is equal to v and n is equal to u. So in this equation, I'll be replacing n is equal to u and m is equal to v. Like after replacing that, we got the equation like this. The integral over the region C f of z dz is equal to double integral over the region R minus dou v by dou x minus dou u by dou y into dx dy plus I into double integral over the region R dou u by dou x minus dou v by dou y into dx dy. So now I am going to use CR equations to make the equation 0. So I'll be using dou u by dou x is equal to dou v by dou y. So in this equation, I'm going to replace dou u by dou x is equal to dou v by dou y. And here in this equation, I'm going to replace dou v by dou x is equal to minus dou u by dou y. Now after replacing this CR equation in the above expression, we got the expression like this. Integral over the region C f of z dz is equal to double integral over the region R minus dou v by dou x plus dou v by dou x into dx dy plus I times of double integral over the region R dou u by dou x minus dou u by dou x into dx dy. So this term gets eliminated. This term gets eliminated. It will become 0. So I got the integral over the region C f of z dz is equal to 0 plus I0. So I got the integral over the region C f of z dz is equal to 0. Hence the Cauchy's theorem has been proved. So next is consequences of Cauchy's theorem. The first consequence of Cauchy's theorem is, if f of z is analytic in a region R and if P and Q are any 2 points in the same plane and the same region R, then the integral between the points P to Q f of z dz is independent of the path joining P and Q. That is, the integral between P and Q, f of z dz is same for all curves joining P and Q. So it is given by the integral over the region C1 f of z dz will be equal to the integral over the region C2 f of z dz. So this can be explained in the figure also. So in the XOY plane, I'm taking a curve PQ, and this curve PQ has been divided into two parts. One curve is C1 and one more curve is C2. Now the integral over the region C1 f of z dz will be equal to the integral over the region C2 f of z dz. That the total area of the curve C1 will be equal to the total area of the curve C2 we can tell. Consequence number 2. If C1 and C2 are two simple closed curves such that C2 lies entirely within C1, and if f of z is analytic on C1 and C2 and in the region bounded by C1 and C2 also, then the integral over the region C1 f of z dz will be equal to the integral over the region C2 f of z dz. So I'm taking an XOY plane. In the XOY plane, I'm taking two curves C1 and C2. The C2 curve lies entirely within C1. Then the total area of the curve C1 will be equal to the total area of the curve C2. Third consequence, if C is a simple closed curve enclosing non-overlapping simple closed curves C1, C2, etc., etc., Cn, and if the function f of z is analytic in the annular region between C and these curves, then the integral over the region C f of z dz will be equal to integral over the region C1 f of z dz plus the integral over the region C2 f of z dz plus so on, plus the integral over the region Cn f of z dz. So I'm taking XOY plane. This XOY plane contains a curve C, and this curve C having n number of curves like C1, C2, C3, Cn. So then the total area of the curve C will be equal to the total area of the curve C1 plus C2 plus Cn and so on. Now problems on Cauchy's theorem. The first problem is verify Cauchy's theorem for the function f of z is equal to z square, where C is the square having vertices 0, 0, 1, 0, 1, 1 and 0, 1. So to prove Cauchy's theorem, we have to get answer 0. Then only we can say the function satisfying Cauchy's theorem here. So the given function is z square. So z square, in the sense I'll be taking the function x plus iy whole square, it will become x square minus y square plus 2ixy. So since the curve C is a square with the vertices 0, 0, 1, 0, 1, 1, 0, 1, I'm plotting that. So in the XOY plane, I'm taking the point 0, 0 at origin. The point 1, 0 I took in the positive x axis. The point 0, 1 I took in the positive y axis. I took 1, 1 point here. So calling this point as 0, this point as A, this point as B and this point as C, and joining all this point OA, AB, BC and CO. Now I am assuming that the curve C is moving from the region O to A to B, B to C and C to O. So in the region O to A, we have to observe that the common point at O is 0 and A also 0 only. So in this plane I will be taking y is equal to 0. It implies dy will be equal to 0. The limit for x will be 0 to 1. And in the region AB, the common point is x is equal to 1. At the point A, we have 1, 0. At the point we have B, we have 1, 1. The common point is x is equal to 1. Dx will become 0. So since dx is 0 means only dy will be there. So we have to find y limit. So here y varies from 0 to 1. And in the region BC, the common point is y is equal to 1. So y is equal to 1 means dy will be equal to 0. We have to find the limit for x. So in this region, the x varies from 1 to 0. And in the region CO, the common point is x is equal to 0. X 0 means dx will be equal to 0. So we have to find the limit for y. So here y varies from 1 to 0. So now the curve C has been divided into 4 regions like OA, AB, BC, CO. So therefore it will become what? The integral over the region OA z square dz plus the integral over the region AB z square dz plus the integral over the region BC z square dz plus the integral over the region CO z square dz is equal to 0. Since we have we know that z is equal to x plus iy and dz is dx plus idy. So z square dz will become x plus iy whole square into dx plus idy. Now along the region OA, we have the point y is equal to 0. It implies dy is equal to 0 and x varies from 0 to 1. So now I'll be replacing these points in the above equation. We'll be getting the integration OA z square dz will become the integral x from 0 to 1 x square dx, because I'm replacing y is equal to 0, dy is 0 here, so I got only x square dx. Like after integration, I got the equation x cube by 3 with the limit 0 to 1, I got the value 1 by 3. Similarly, in the region AB, we have the common point x is equal to 1. It implies dx is equal to 0. Since dx 0, we have to find only y limit. So here y varies from 0 to 1. So in the equation, if I replace x is equal to 1 and dx 0, I got the equation like this. The integral over the region AB, z square dz will be equal to the integral y from 0 to 1, 1 plus iy whole square into I dy. So it will become I into integral y from 0 to 1, 1 minus y square plus 2 iy. After expanding this, because I square is minus 1, I got this equation. Now after integration, this equation will be getting I into y minus y cube by 3 plus 2i y square by 2 with the limit 0 to 1. Applying the upper limit, I'll be getting I into 1 minus 1 by 3 plus I. For lower limit, it is 0. By simplifying this, we got I into 2 by 3 plus I. It will become 2 by 3 I minus 1. Now in the region BC, we have y is equal to 1. It implies dy is equal to 0. Since dy is 0, we have to find only x limit. So in this region, x varies from 1 to 0. So we got the equation, the integral BC z square dz will become integral x from 1 to 0 x plus I whole square dx. Expanding this, we got x square minus 1 plus 2ix dx. This is because of I square is equal to minus 1. So we got the integral x from 1 to 0 x square minus 1 plus 2ix dx. So it will become x cube by 3 minus x plus 2ix square by 2 with the limit 1 to 0. Now after applying the upper limit, it will become 0. For lower limit is minus of 1 by 3 minus 1 plus I. So I got the value 2 by 3 minus I for this region. Now the last region along CO. Along CO we have x is equal to 0. It implies dx is equal to 0 we have. Since dx is 0, we have to find only y limit. So in this region, y varies from 1 to 0. So now the integral over the region CO, z square dz will become integral y from 1 to 0 iy whole square into I dy. So it will become what? Minus I, because I square is minus 1 with the integral y from 1 to 0 y square dy. Like after integration, I got the equation like minus of I into y cube by 3, the limit 1 to 0. For upper limit, it is 0. For lower limit, it is 1 by 3. So I got minus I into 0 minus 1 by 3. So I got the equation, the integral over the region CO z square dz will be equal to I by 3. So now I'm going to replace all these equations in the main equation. I got the equation like this. Integral over the region OA z square dz plus integration over the region AB z square dz plus integration over the region BC z square dz plus the integration over the region CO z square dz will be equal to 1 by 3 plus 2 by 3 I minus 1 plus 2 by 3 minus I plus I by 3 is equal to 0. After simplifying this, we'll be getting the answer 0. So hence we can say that the Cauchy's theorem has been verified. So in the next lecture video, we'll be discussing the Cauchy's integral formula and problems on Cauchy's integral formula. Thank you.